turbomachinery working process, we will use 4 energy corrosion, 4 different shape of energy corrosion. One shape of the energy corrosion, it was Bernoulli corrosion. Today I'm plan to discuss additional 3 shape of the energy corrosion. It will be energy corrosion in mechanical form in relative motion. I refresh what the Bernoulli corrosion was in absolute motion. I want to discuss 2 shape of the energy corrosion in heat form, in absolute motion and in relative motion. Of course, I hope you are already studying this corrosion in previous courses, like gas dynamic, like thermodynamic, but I'm only refresh to you how we receive these formulas, and of course we will pay more attention about the application of this corrosion to the turbomachinery working process, and I forgot the word. What I want to say. We are trying to achieve some important conclusion deal with the working process of the turbomachinery and gas turbine engine, of course, too. And I hope it's will help to us to better understand the construction and working process of the turbomachinery and gas turbine engine. Okay, let's start. If we will have time, if we will have additional time, we will start to study momentum conservation equation. So it's our plan for today, but I think we will only investigate 3 energy equations. So, okay, let's start the lecture. I will share my screen. So, do you see the presentation?
Yes.
Perfect. So, we will receive the energy corrosion in mechanical form in relative motion. So, the process of receiving of this corrosion in common the same like for the Bernoulli corrosion. So, you see the approximately the same picture like in the case of the Bernoulli corrosion, but of course it will be a little bit different corrosion. So we have let's study the working process of the random turbomachinery, but if in the case of the Bernoulli corrosion it was really random turbomachinery, really random blade row, it was not big importance what kind of the blade row we have, rotor wheel or guide vane or nozzle blade. It will be not important for the Bernoulli corrosion. At this case, in the case of energy corrosion in mechanical form in relative motion, we will take the moving blade row. By other words, it will be rotor wheel. So, we take random rotor wheel of the turbomachinery, and we take the random particles which flow near. Is it works? 1 second. Which will flow near the surface of the blade. These particles have name A, move with the relative velocity W. W it's the velocity in the relative coordinate system which are rotate with the rotor wheel. Okay. And these particles are moving along relative trajectory in relative motion as W. So let's choose the let's choose the local coordinate system. At this point A, the first x will be direct along the direction of the particle velocity in relative motion w, this one. The second x will be normal to the first one, and the last it will have name nw. And the last x will be normal to the previous two. It will be xlw, and this x normal to xsw and nw. So we will take part of the space around the point A. Which will be look like the brick. This the sizes dl, dn, and ds, and we extract this brick, and because we don't want to change everything, we replace the action of an environment by action of the forces. So that's why we need to find what kind of forces are impact to this brick in the case which we are investigating. One additional information. Of course, because we know density and because we know volume, we could to calculate volume of this brick, we could to find the mass of this volume. This is density, rho, dn multiplying ds multiplying dl, of course. It's very simple, I think you understand. So, what kind of forces are impact to this brick? In the brick are rotating in a relative coordinate system. Of course, on the brick we have influence of the same force which we have in the case of the Bernoulli equation in absolute motion. It was the pressure force. Here I mean resulting pressure force. I refresh the information for you. What we have different, in common case, we have the different pressure which impact to all side of the brick. For example, to the side dn, dl, we have the action of the pressure P. To the opposite side of the brick, which are located at the distance SW relative the first area, we have impact of the pressure P plus dp. It means what the pressure could be changed along the x SW, and the same for the other four sides of the brick. We have some pressure which impact, for example, to the side dn ds, and in common case it will be different pressure relative this pressure, and we have other pressure P plus dp which impact to the opposite side. That's why we have influence of the pressure different force, the results in pressure different force, because in common case pressure will be changed in all direction of our space. The second force, resistance force. So you know what when the particle moves along the path line, we have acting of the resistance force. It's the force of hydraulical resistance, and usually these force are direct in the direction of the velocity, but in opposite side. That's why the force dt, resistance force will be direct to the opposite side relative velocity, or relative velocity. So the next moment we have force which are force with which the blade acts to the flow, and these three force, I mean this one, and this one, was in the case of the Bernoulli equation. So, but here we are looking, we are investigating the action in relative motion. That's why we need to add inertia forces in our investigation. What kind of inertia forces we have at this case? We have centrifugal force, and it's direct along the rails. This one, this is Coriolis force. I remember to you what the Coriolis force direct normally to the x of rotation, and at the same time normally to the direction of the velocity w. That's why the direction of Coriolis force will be like here. It's normal to the normal to the direction of rotational x, and normal to the direction of the direction of the relative force. So let's write these five forces. It's all forces which impact to our brig. So let's write the second Newton's law applying to this case. At our case, in the case of relative motion, it will be not directly second Newton law. It will be D'Alembert equation. It's one of the shape of the second Newton's law for moving coordinate system. So we could to write Newton's second law, by other words, it's D'Alembert equation, and this equation says to us what assume of all external forces, these three, because it's the forces from the pressure difference, forces which impact from the blades, and resistance force, plus inertia force, are equal to the mass multiplying to the acceleration in relative motion. It's the Newton's second law for the relative motion. By other words, it's the D'Alembert formula, D'Alembert equation. Of course, this is vector equation, and it's not very convenient to work with the vector equation. That's why we will project our equation. I mean Newton's second law to the x as w, like in the case of the Bernoulli equation. So what we have in the projection of the x as w? Because Coriolis force are normal to the direction of the w, that's why Coriolis force are not project to this x. That's why we are neglected. The second moment, in relative motion, the forces with which the blade acts on the flow are not create the specific work. That's why we will not take in account this force, because it's not it's not produce the specific work in relative motion. That's why we will not take it in account. So about the pressure, what I want to say, 1 second. One second. About the forces from the pressure, like in the case of the Bernoulli equation, we are find force which impact to this side of the brick and to the force which impact to this side of the brick. Other sides of the brick are not create the projection to the XSW. That's why we could to write the pressure from this side like P multiplying to the area of this side of the brick. It's equal to dN multiplying to dl, and the same from the opposite side of the brick. P plus dP multiplying to dN to dl. After some conversation, we receive such equation. So the resistance force project to the XSW without any distortion. It's project in real length, and the same we could to say about velocity W, because resistance force and relative velocity are direct along the XSW. Centrifugal force will be project to the SW direction using such equation. So we are multiplying all parts of this equation to the ds and divided by mass dm. You could to see what some of elements of formula will be disappear, like in the case of the Bernoulli equation. And here at the right part of the formula you see distance divided by time, its relative velocity, multiplying to the relative velocity. So finally, after all conversation, we receive such equation. Let's try to understand the physical mention of all terms of this equation. First of all, this part and this part of this equation we are already discussed when we was speak about Bernoulli equation. Let's remember this term. It's the work on the pressure change in the turbomachinery. It's the energy, it's the mechanical work which we are spent to increase pressure or decrease pressure in the turbomachinery. The last term we are already have it in Bernoulli equation. This is specific work for overcoming losses. If we will speak about the second right term, you could to see what this term looks like change of kinetic energy. W2 divided by 2, it's the changing of kinetic energy. But in our case, we have relative velocity. We have letter W, what's mean relative velocity. And that's why finally we speak about the changing of kinetic energy in relative motion. And the left term looks like change of kinetic energy, and this term, this is specific work of inertial forces. So let's integrate this equation, and finally we receive classical shape of energy equation in mechanical form in relative motion. I hope what you are already received this equation in previous courses like gas dynamics, but sometimes students are not study this equation in the course of gas dynamic. That's why maybe you never see this equation before. But as you are see in few minutes in the future, these equations are very important for turbomachinery, for understanding of the working process of the turbomachinery. And I hope you are already study this equation in the course of gas dynamic, and I hope it will be give to you possibility to more easy understand this equation. So, in any case, we are receive energy equation in mechanical form in relative motion, and this is classical shape of this equation. Let's write this equation for the compressor. How we will write it? Very easy. You see what we have the term which are describe the pressure change in the compressor. That's why we are move this part to the left shape of the formula, and we are move all velocity to the right shape of the formula. And finally, we are receive such equation for the compressor. It's really very important equation because it lays on the base of the principle of operating of the compressor. Let's try to find the conclusion. Let's try to explain what this equation want to say for us. For these purposes, let's simply read this equation step by step. So, what we could to say, look into this equation. Pressure change in the compressor take place due to of the movement of the working fluid in the field of action of inertia forces. It's the first term. And breaking the flow in relative motion, contrary to hydraulical resistance. So it's really very important because this equation says to us what the pressure in the compressor are increased because we have acting of inertia forces in the compressor, and we have the breaking flow in relative motion in the rotor wheel. Why I say about the breaking the flow? It's very easy to understand if you look to this term. If this term will be positive, and it means the pressure will be increased if W1 will be more than W2. So it means you are receive pressure increase in pressure if W1 will be more than W2. By other words, you will break the flow in relative motion. So it's really important equation. We will discuss it a few minutes in the future, but you understand what this equation explain why the pressure are increased in compressor. And of course the second question, how to realize it in real construction, but we will discuss it in the next chapter. Okay, let's apply this equation to the turbine, and finally in the turbine we receive the same equation. This equation say to us what the work of the gas expansion on the turbine goes to overcoming of inertia forces and increasing of kinetic energy in the motion and overcoming of hydraulical resistance. So this equation describes to which direction we are spent energy of expansion of the gas expansion in the turbine. So what I want to say, and I pay your attention what this equation for the compressor and for the turbine looks very similar. I think you understand what if we compare these two equations, we will find only one difference between this equation. Uh, only sign. Um, you could to imagine what you are multiplying this equation to -1, and finally you are receive this equation. But one problem at this sign, it will be it will be okay. So I pay you attention what we will very often to find the situation, what the equation for the compressors and for the turbine will be very similar, and they will have only one difference. You are multiplying one equation to -1 and receive the equation for the turbine. Okay, let's remember what kind of the compressor we are know. We know two type of the compressor. We know centrifugal compressor, and the main feature of this compressor, what the air comes inside, comes into the compressor in the lower radius and move from axial direction to the radial direction and comes out to the upper radius. So we could to say what R1 more than R2. We are sorry, it's mistake. So we could to say what R2 more than R1. By other words, the air comes in inside the compressor in lower radius and comes out from the compressor to the upper radius. What it gives for us? It's give what circumferential velocity at the outlet of the rotor will be more than circumferential velocity in the inlet of the rotor wheel. And finally, it's mean what the first term of the right part of the energy equation in mechanical form in relative motion will be positive. It's mean what inertial forces in centrifugal compressor take place into the compression process. So, and finally, we could to say what the energy equation in mechanical form in relative motion are writing for the compressors, I mean, are writing for the centrifugal compressor. So we could to say what the equation for the centrifugal compressor will be looks like here. dP divided by rho equal to So this is shape of energy equation in mechanical form in relative motion for the centrifugal compressor, but we are discuss what is the common shape of this equation for the common compressor. So what we could to say about the axial compressor? In the axial compressor, the air comes inside the rotor in the radius R1 and comes out move along the rotor wheel approximately in the direction parallel to the direction of the x of rotation and comes out approximately to the same radius. So in the axial compressor, the main feature of axial compressor, what the flows move along the compressor approximately in the direction approximately parallel to the x of rotation. That's why it's come into the radius R1 and comes out to the radius R2, but because the direction of the vectors of the velocity approximately parallel to the direction of x of rotation, we could to say what R1 approximately equal to R2. And finally, it leads what the circumferential velocity in the inlet of rotor and at the outlet of rotor approximately equal. And it's mean what the first term of energy equation in mechanical form and relative motion for the compressor will be leads to the zero. And finally, we are receive what the for axial compressor, this equation will be looks like here. So it's like in the case of the centrifugal compressor, but the first term leads to zero. That's why we are remove it from the formula. So what's the main conclusion here? In the centrifugal forces, in the centrifugal compressor, the pressure increase because we have action of inertia forces and the flow deceleration in relative motion. So we have two reasons of increasing pressure. If we will speak about the axial compressor, the pressure in the axial compressor increase only because we have flow deceleration in relative motion. It's really very interesting. We have two different reasons. Of course, they are similar reasons, but we have different reasons of increasing pressure in centrifugal compressor and axial compressor. It's the first idea. The second idea, you see what the flow deceleration in relative motion, it's the common reason of increasing pressure in both type of the compressor. That's why let's draw the scheme. So axial compressor, centrifugal compressor. So, and let's draw the part of energy which we are supplying for increasing pressure. In both cases, we are supplying for increasing pressure changing of kinetic energy in relative motion. And let's imagine what this part approximately equal for both type of the compressor. But in the case of the centrifugal compressor, we are additionally add this part. We are additionally add this term. We are additionally add action of inertia forces. And let's remember, and we have now this term in the case of axial compressor. And let's remember what the maximum pressure ratio we could to reach in axial compressor. Approximately 2. This is pressure ratio. At one stage, I mean, of course. And what the maximum pressure ratio we could to receive in one stage of centrifugal compressor, we already discussed it when we speak about the classification. Approximately 10. What it mean? It mean what this part of energy, it's two pieces, two units of energy. And this part of energy, the green one, it's the 8 units of energy. So, by other words, what I want to say to you, in the axial compressor, for increasing pressure, we are supplying only flow deceleration in relative motion. And simply says it's 2 units, 2 pieces of energy, which we are spent for increasing pressure. In the centrifugal compressor, we are changing kinetic energy in relative motion for increasing pressure, and it's approximately 2 units of energy for increasing pressure, but additionally we are at action of inertial forces. And action of inertial forces could be reach 8 units of energy. You see what in the centrifugal compressor we are supplying more energy for increasing pressure. That's why finally pressure ratio of axial compressor are lower than the pressure ratio in centrifugal compressor. It's very important conclusion here because it's explain why the pressure ratio in centrifugal compressor more than pressure ratio than in axial compressor. And the last idea, okay, let's imagine what we have centripetal compressor. One second, let's use this one. Let's imagine we have centripetal compressor. In centripetal compressor, the flow wheel becomes inside a rotor wheel at upper radius and comes out to the lower radius. It will be R2, it will be R1. It's mean what R1 more than R2, and it's mean what U1 lower than, sorry, not lower, it's more. U1 more than U2, and it's mean what this term for the centripetal compressor will be negative. That's why let's add the scheme for the centripetal compressor. We are add the energy because we decelerate the flow in relative motion, and we need to add this term. But at the case of the centripetal compressor, this term will be negative. That's why we need to extract it from the energy which we are supplying for the compression. So, by other words, we need to minus this energy. And I hope you understand this scheme. I hope. And you see what the finally, we are not, in the case of centripetal compressor, we are not supply energy to the compression. We are extract energy from the flow, and that's why finally we are not receive the pressure ratio. That's why you are never meet the centripetal compressor. Of course, we could do meet the compressor at which radius a little bit reduced, but usually the value of reducing of the radius is not so much, because if you will reduce radius in the compressor so much, you are not receive the pressure rise. So I think it's very important slide. It's explain why we are increasing pressure in centrifugal compressor, because we have action of inertial forces and flow deceleration in relative motion. And it's explain why the pressure increase in the case of axial compressor, because the flow decelerated in relative motion. This slide I show because we are supplying different quantity of energy for the compression in different type of the compressors. The pressure ratio of one stage of axial compressor will be lower than the pressure ratio of centrifugal compressor. And finally, we explain why centripetal compressors are not used in wide practice. I think it's a very important conclusion which we are received using mechanical energy equation in mechanical form in relative motion. So, okay, let's come further. So, like in the case of the Bernoulli equation, let's take the energy equation and let's put this term inside the integral sign, and we are refresh what this formula is: the total pressure of the flow stagnating in relative motion. And using this information, finally we are good to convert energy equation in mechanical form in relative motion to the such shape. This equation could be used for recalculating of parameters between the first and the second section, in the case then you are calculating the turbomachinery stage. So it's very important. Usually during calculating of the turbomachinery, you could to calculate parameters in the inlet of the rotor wheel, and you need to transfer the information to the section at the outlet of the rotor wheel, and these equations are really used to recalculate parameters from the inlet section of the rotor wheel to the outlet section of the rotor wheel. So, what we could to say looking to this equation? We could to say what the total pressure of the flow stagnating in relative motion will be changed only in the case if you will move in the field of the action of inertia force. By other words, if you will change the radius inside your rotor wheel. And of course, this value are depend from the losses. So what else? Let's set the new parameter. The pressure of the flow stagnated in the rotor wheel. You see how to receive this parameter. P omega with the star, it's the P W with the star minus 0.5 density multiplying to the circumferential velocity at the second degree. So if we will put this new parameter to the energy equation in mechanical form in relative motion, finally we receive this equation. It's really very interesting equation because it's always convenient to have the parameters which doesn't change during process. And you see what in the case if you have no losses, this parameter will be equal to the zero in any case. So in any rotor wheel of the turbomachinery, in the case of ideal flow, in the case if you have no hydraulical resistance, this element will be always equal to zero. And it's mean what the value of P, omega and star will be constant in the rotor wheel, but in the case of ideal flow. Of course, in reality, you see what in this equation we have losses. It's mean what the losses will be impact to the value of the pressure of the flow stagnated in the rotor wheel. And it's mean what we could to use total pressure recovery coefficient to describe the perfection, hydraulical perfection of the rotor. it's the same approach like in the case of non-moving channels, which we are discussed when we are speak about Bernoulli equation. Sorry. And the last, not last conclusion. Let's take the energy equation in mechanical form in relative motion, and we are extract change energy of the change of the pressure using this equation for the compressor and for the turbine, and put inside the Bernoulli equation. I hope you remember what the second equation, it's the Bernoulli equation for the compressor and for the turbine. So we will take the integral and put inside the Bernoulli equation. And finally we receive these two formulas. What we could to find if we will look carefully to this equation. First of all, let's try to simply read information which are set at this equation. Let's discuss the equation for the compressor. Mechanical work which are supplying in the compressor are spent on the increasing kinetic energy in absolute motion, this one, and pressure increase due to the action of centrifugal forces. It's the it's the second term, and pressure increase due to the flow deceleration in relative motion. It's the last term. So maybe this conclusion looks boring, but this conclusion I explain to which direction you are spent mechanical energy which you are supplying inside the compressor. So you are spent mechanical energy to increase in kinetic energy in mechanical motion, to increase in pressure due to action of the centrifugal forces, and increase in pressure due to the flow deceleration in relative motion. And the same for the turbine. Specific theoretical work done by gas on the blades of the turbine rotor wheel is obtained because we are changing kinetic energy in the nozzle blade, it's the first term, and in the rotor wheel it's the last term, and because we have action of centrifugal forces it's the second term. Of course, you could think what these two conclusions are rather boring, and maybe it's not clear how to use it in real practice, how to explain something in the working process of the turbomachinery. And I think it's more interesting to compare these two equations. You see what these two equations, one for the compressor and the second for the turbine, really the same. Only one difference between it, we are already discussed it. You need to multiply the first equation to the -1 to receive the second equation. It's really typical for the formulas for the compressor and for the turbine. In future, you will see using other equation what it's really very typical. What for the compressor and for the turbine we are using the same equation with only one difference. One equation multiplying to -1. It's the equation for the turbine or equation for the compressor. It's really very typical what we are using the same equation for the compressor and for the turbine, but with only one difference, the equation for the compressor multiplying to -1, and we are receiving the equation for the turbine. What it means? It's mean what the compressors and the turbines are using the same physical principles in the base of the operating process. So it's mean what compressors in the turbine have the same physical base of the working process. But because we are multiplying equation to the -1, we could to say what the working process of the compressor and the turbine are opposite. So we have the same physical base of the working process of the compressors and the turbines, but the working process of the compressors and the turbines are opposite. If in the case of the compressor we have the flow deceleration, in the turbine we have the opposite process, we have acceleration of the flow. If in the compressors we have increasing pressure, in the turbine we have opposite process, we have gas expansion process. And what it's mean? It's mean what we could to take compressor and, for example, receive the pressure difference between the inlet and the outlet. For example, we take the rotor wheel of the centrifugal compressor or axle, it's not important. And we are creating pressure difference between the inlet and at the outlet. For example, here we put high pressure, here we put low pressure. And I think this compressor, at the case when we are creating the pressure difference between two sections, will be work like turbine. It will be create mechanical work. And at the opposite case, if we will rotor wheel turbine, and if we will supply mechanical work, it will be increased pressure. But of course, the main question at this case, what the efficiency of such process. But if we are rotate the working process of the compressor or the turbine to the 180 degrees, we receive the opposite machine. I think it's wonder. And the last idea deal with the energy equation in mechanical form in relative motion. At previous slide, we receive such relationship. And this work, it's the mechanical work which are supplying from the blades to the compressor. This work are called theoretical specific work. But it's very interesting. Very interesting case. What in the compressor usually for designating specific work use term head. It's only traditional. We will find a lot of examples then the guys which work with the compressor and guys which works with the turbine use different names, different designation for the one physical value. And at this case, we are speaking about specific work, but in the compressor, it's traditional. It's simple traditional to use term head to designate specific work, but in reality, it's a specific work. So this equation, which we are discussed in previous slide, describe the mechanical work which are supplying by blades to the flow. Let's set the new names. Let's take the first term of this equation. You will see what is the change of the kinetic energy in absolute motion. This specific work are called dynamic head. Dynamic head. It's the change of kinetic energy in absolute motion. Usually, this specific work are converted to the pressure in the in the guide vane. Say this energy are converted to the pressure in guide vane, in non-moving blade row. Changing of pressure, changing of potential energy of the flow are described by energy equation in mechanical form in relative motion, and this specific work are called static head. It's the change of potential energy of the flow. By other words, the dynamic head, it's the change of kinetic energy of the flow. The static head, it's the change of potential energy of the flow. And this conversation of energy take place in the rotor wheel. So we could to say what this type of mechanical energy converted to the pressure increment in the guide vane, and this energy are converted to the pressure ratio in the rotor wheel. The rotor wheel, it's the guide vane. If we will compare these two equations, this the equation for theoretical head, we are simply find the relationship between the theoretical head, dynamic head, static head, and resistance. So, and let's remember how the compressor operates. We are supplying mechanical specific work, mechanical head, and this work are called internal head. It's the mechanical energy which are supplying to for the operating of the compressor. This energy are transferred to the blades, and the energy which are get to the blades are called theoretical head, finally, and this energy, theoretical head, I mean, are transferred to the flow by blades, and finally you receive the pressure ratio. At all moments, at all steps, we have some losses, and based to this information, we could to imagine the process of the energy transfer in the stage of the compressor. How the energy are converted to the change of the kinetic energy and to the change of the potential energy of the flow in the compressor stage. So you are supplying this specific work from outside, from the turbine, for example, to the compressor. Because you have friction on the back sides of the discs, because you have non-returnable leakages, you lose some of supplying energy to overcome resistance of rotating of the disc of the turbine, and you lose some energy with the leakages. The energy which you are not lose during energy transfer from the source of energy to the blades are called the theoretical head, and this energy are supplying to the flow. You are supply this energy, this specific work, to the flow by blades, and this energy are spent to overcome hydraulical losses in the flow path of the compressor, and the energy which you are not lose to overcome losses are spent to changing of kinetic energy of the flow, by other words, to change of to the creating of dynamic head, and of this energy are spent to the changing of potential energy of the flow, by other words, to the creating of the static head. The same analysis we could do perform for the turbine. In the turbine, we are split the mechanical, split the theoretical head to two parts. This part, dynamic specific work. This energy, this energy of the flow are transferred to the mechanical work, mostly in the nozzle guide vane, and this part, static specific work, are transferred to the mechanical work in the rotor wheel, mostly in the rotor wheel. And like in the case of the compressor, we could to find the relationship between the theoretical specific work and dynamic specific work and static specific work and losses. And finally, we could to find the energy exchange process in the turbine. What the process are realized in the turbine? In the turbine, we have expansion process in the rotor wheel, and from one hand we have changing of potential energy, we have expansion process, and from other hand we have changing of kinetic energy of the flow which flows through the turbine. Because we are change kinetic energy of the flow, and because we are change potential energy of the flow, finally we are receive such quantity of the energy. So, by other words, we have process of changing of kinetic energy and process of the changing of potential energy in the flow path of the turbine. Because we are change kinetic energy and because we are change potential energy, finally we are receive such quantity of the energy. Some part of this energy are spent to overcome hydraulic, and we are lose this energy to overcome hydraulic losses, and all energy which we are not lose to overcome hydraulic losses are catched by blades. So this theoretical specific work are catched by blades in the turbine. Of course, not all this energy are convert to the useful work in the turbine and supplying to the compressor, for example. Some energy are spent to these the leakages, and some energy are spent to overcome friction or between the gases and disc of the rotor wheel, which are breaking the flow. So, and the energy which we are not lose to the disc friction and which we are not lose to these leakages are called internal specific work, and exact this energy are supplying to the compressor, which are driven by turbine. So, I think that's all for the energy equation in mechanical form in relative motion. Do you have any questions deal with such equation? So, you see it's very important equation, and we make a lot of conclusion deal with the turbomachinery. So, we are discussed the energy exchange process in the stage of the compressor and at the stage of the turbine. We explain why the pressure ratio of the centrifugal compressor more than pressure ratio of axial compressor, and we discuss a lot of other important conclusions. Do you have any questions deal with the energy equation in mechanical form and relative motion?
I have a question, but I don't know really how to explain. But last year in construction of engine, we saw that in order to increase the pressure, we had to have divergent channel in the compressor stage and convergent channel in turbine. So how it's taken in account in those equations?
So you mean this type of the channel in the compressor, yes or no? Or you mean the channel between the blades?
No, channel between the blades.
Channel between the blades. Perfect. If we will take this equation for the compressor, you could to find what we need to break the flow. And the next question, how to realize it in real construction. So, if you look carefully to this equation, you will find what if you want to increase the pressure, you need to realize what the W1 must be more than W2. It means you need to create you need to break the flow, you need to reduce the velocity of the flow. And how to realize it? Very simple, you need to use diffuser channel, you need to organize diffuser channel which will be divergent. So I don't know how to explain, but so based on this equation, we need to answer how to realize this principle in the construction. If we will speak about first term, it means what you need to organize what U2 must be more than U1, and it means what outlet radius must be more than inlet radius. And U comes to the scheme of the centrifugal compressor. Then U comes into the low diameter and comes out to the upper diameter. So use difference of the diameter, you could to use this term to increase in pressure. For using this term for increase in pressure, you need to break the flow. And how to break the flow? You need to use a divergent channel. It's okay?
Yes, it's clear. Thank you.
We will repeat it when we will speak about the principle of operating of compressor stage and the turbine stage. So after the finishing of this chapter, I will discuss with you principle of operating of the turbine and the compressor. In reality, it will be the same information like at this chapter, but it will be concentrate information about the compressor working process and about the turbine working process. And we will assume all information from all equation which we are discuss. And I hope it will be set all information about the working process of the turbine and the compressor, and you are clear understand the working process. But it's really the basic equation of understanding of the working process of the compressor. You see, it's explain why the pressure increase, and the second question, how to realize it in construction. So, do you have any other questions? No? Okay, we have some time, and let's study one small energy equation. It will be energy equation in in heat form in absolute motion. It will be a not long discussion. I believe what you are knowing this equation and you are received in thermodynamic course and gas dynamic course. So let's take Bernoulli equation in differential shape and make only one change. We are replace density to the specific volume. I hope you are remember what the density is, the one divided to the specific volume. So in ideal case, the working process in the turbomachinery take place without supplying external heat and internal heat too. So in ideal case, we are not supplying heat in the turbomachinery working process. But of course, in real process, we have supplying heat. And what the source of the heat in the real process? The source of the heat in the real process is hydraulic losses, because finally all losses, all hydraulic losses became the friction. And you know, if we realize the friction, we will feel the warm. So it means what the friction are convert to the heat, convert to the warm. And in reality, we have source of the heat in our process, and this source of the heat is hydraulic losses. All hydraulic losses finally will convert to the heat which will be supplying to our process. So, it's the first idea. Let's write the equation of the first thermodynamic law. It will be looks like at this formula, and this law says to us what all supplying heat, it means external heat and internal heat, are spent to the change of the volume and increasing of internal energy of the thermodynamic system. So in our case, we have internal source of energy, and this internal source of energy equal to the energy which we are spent to overcome hydraulic losses. That's why we will think what this internal energy equal to the specific work which we are spent to overcome hydraulic losses, and we extract this value from the equation of the first thermodynamic law, and we are put it inside to the Bernoulli equation. Finally, we receive such equation. First two terms, it's the enthalpy. That's why we could receive this equation. And after integrating process, we receive this equation, which are called energy equation in heat form in absolute motion. So I hope you know this equation, and I hope you remember what enthalpy plus kinetic energy of the flow. It's the total enthalpy or enthalpy of stagnated flow. What the conclusions we could to receive based to this equation? First of all, let's sorry, 1 second. Let's hide this part of equation, and let's read this part of equation. What we receive if we will simply read this equation? Supplying heat, supplying external heat and mechanical work in the process are used for the changing of enthalpy, by other words, a changing of internal energy of the flow and changing of kinetic energy of the flow. It's the first conclusion. The second conclusion, one second. Let's erase this part of the equation. And we are simply read, maybe it's better to erase this part too. Maybe we are simply read this equation without middle part. What we could say about this equation? Total temperature will be changed only in the case if you are supplying or extracting heat and mechanical work. It's really very interesting conclusion. It shows to us at which case we will change total temperature. Total temperature will be changed only in the case when you are supplying or extracting heat, it means external heat, and mechanical energy. In the turbomachinery, we have no supplying heat. We have no heat exchangers, we have no combustion in the turbomachinery. That's why in the turbomachinery, we could erase this part, and finally, for the turbomachinery, we receive what the total temperature will be changed only in the case if you are supplying or extracting mechanical work. And when we are supplying mechanical work, when we have physical motion, when we have physical action, and it's mean what the total temperature will be changed only in the elements which are moved. And in the turbomachinery, we have moving only in the rotor wheel. By other words, total temperature will be changed only in the rotor wheel. So, in rotor wheel, total temperature will be variable. In non-moving channel, in guide vane, in EGV, inlet guide vane, in nozzle guide vane, in nozzle blades, total temperature will be constant. So, if you remember the Bernoulli equation, the total temperature, the changing of the total temperature looks like the changing of the total pressure. But if we will return back to the total pressure, I will try to return back very fast, we'll find if you return back to the total pressure, you will find what the total pressure we have two differences between the changing of the total pressure and total temperature. So I refresh to you what the total temperature will change if you are supplying heat and supplying mechanical energy. And if you look carefully to this equation, total pressure will be changed only in the case if you are supplying mechanical work. So it means what total temperature depends from the heat, total pressure do not depend from the heat. It's the first difference. And the second difference, in the equation for the total pressure, we have losses. Of course, losses have influence to the energy equation in heat form, but the heat of the losses allocated inside your system, and that's why total enthalpy and total temperature will be not change. In the case of the total pressure, losses will have influence to the total pressure. That's why if you have losses, total pressure will be a little bit drop, but total temperature will be constant. So, simply says, the total temperature will be changed like total pressure, but we have two differences. Total pressure do not depend from the supplying heat, and total pressure depend from the losses. Total temperature do not depend from the losses. So guys, I think that's all for today. Do you have any question about the energy quotient in heat form in absolute motion? I know you know this equation because it's really widely used in real practice. Do you have any questions?
No, thank you.
No, perfect. So I think that's all for today. It's enough for today. And we will finish in our lecture. If you have no questions, you could be free. We will meet the French guys in the next Monday at this time. We will meet with the Egyptian guys by timetable. I will write to you the message about the next lecture. So I remember to the guys from the France. Guys, please send to me the results of thermodynamic calculation, and I will try to set to you the methodology of calculating of the flow path of your engine as soon as possible. Okay?
Okay, you want the result we had from Astra?
Yes,
Okay.
it will be perfect. You could send the Astra file, but for me it's more convenient file in Excel.
Excel, okay, yes.
Mhm.
Okay, perfect. I will send it.
Okay, I will wait. So if you have no any other questions, you could be free for today, and I leave the record of today's lecture for you. So thank you for attention. See you at the next lectures.